Hey, you. Think about telling someone the coffee shop is just like a 5-minute walk. Or maybe checking your phone and seeing it's, I don't know, a cool 18 degrees. We're
Mm.
constantly using numbers,
Yeah.
right, to make sense of our day.
Yeah, all the time. And physics, well, it takes this basic idea of using numbers and really pushes it further. It lets us understand the whole universe around us, but with uh, incredible precision.
Exactly. And in physics, these numbers, which, we call numerals, they aren't just abstract symbols floating around.
Not at all. They're really the language we use to describe reality. I mean, at their heart, they are just simple numbers, but in physics, there's this really important extra layer of information. We need to explore that.
Absolutely. So, okay, the goal of this deep dive is to really get to grips with the crucial role these numerals play. We want to show you why there's so much more than just figures on a page.
Yeah.
And we've been looking at some, fundamental explanations of these ideas, stuff that's perfect for building a really solid base.
Exactly. Think of this as our starting point for understanding the quantitative side of the physical world. We'll break down what these numerals are, the different forms they take, and why they are just absolutely essential for making sense of, well, everything from a falling apple to the vastness of space.
Okay, let's dive in then. When we talk about numerals in physics, what are we really talking about?
Well, like you said, at their core, numerals are simply numbers. Physics is fundamentally about measuring things, right?
Okay.
Quantifying the world.
Mm-hmm.
We want to know the speed of something, its weight or mass, how far it travels, its temperature, and for all that, we need numbers, these numerals, to give us that quantitative description.
That makes perfect sense. We're always trying to put a value on what we see. But you mentioned earlier that not all numbers in physics are like the same.
Yeah.
What's the key distinction there?
Exactly. And this is where it gets, well, really interesting. In physics, we generally run into two main types of numerals. First, we have what we sometimes call pure numerals,
Okay.
and then we have numerals with units.
Pure numerals. Okay, that sounds pretty straightforward. What falls into that category?
Yeah, pure numerals are basically numbers that just represent a count. Simple as that. They tell us how many of something exist without any reference to a physical measurement like, length or mass or time.
Ah, okay.
So, for example, if you count 7 stars up in the sky, the number 7 just tells you the quantity. There's no unit of measurement attached to it, really.
Right, so if I say there are 4 tires on a car, or I need 6 eggs for this recipe, those are just counts.
Precisely. Perfect examples of pure numerals. They're kind of like the numbers we first learned back in math class, for counting separate items.
Mm-hmm.
But here's the thing. In physics, just knowing the count often isn't enough. We need to describe the physical properties of things, and, well, that requires more than just a plain number.
And that leads us neatly to the second type, right?
Yeah.
The numerals with units.
Correct, yeah. These are the numerals we use when we're actually measuring something in the physical world. So here, the number is always paired up with a unit. And that unit specifies what kind of measurement we're actually making.
Okay.
For instance, if we describe the length of a table as, say, 2 meters, the 2 is the numeral, obviously, and meters is the unit telling us we're talking about length.
Okay, so like saying the room temperature is 25 degrees Celsius. 25 is the numeral. Degrees Celsius tells us its temperature.
Exactly.
Or if we say a book has a mass of 500 grams, 500 is the number, grams tells us its mass.
You got it. Now think about this. What if I just said the table is 2?
Uh-huh.
Immediately you'd ask, 2 what? Right?
Yeah, absolutely. 2 inches, 2 feet,
Yeah.
2 yards. It's totally vague.
Totally big. So the unit is what provides that essential context. It gives the number its physical meaning.
Oh.
And this brings us to a really, really crucial point. In physics, a number without its unit is kind of like a word without meaning. It's just incomplete. It doesn't fully tell you about the physical reality you're trying to describe.
That's a really clear way to put it. Like, a sentence needs a subject and a verb. A physical measurement needs both the number and the unit. Can you give us maybe another example or two just to really hammer this home?
Sure, sure. Imagine you're following driving directions, right? And they just say, go straight for 10.
10. Yeah, 10 what? Blocks? Miles? Kilometers? You'd have no idea.
Exactly. No idea how far to drive. You could easily get lost. It's useless information.
Definitely frustrating.
Or think about filling up your car. If you went to the attendant and just asked for 30, what would happen?
They'd stare at me. They'd say, 30 what? Gallons. Liters. Dollars worth.
Precisely. Without the unit, the quantity is just meaningless in that context.
So it's not just some, like, arbitrary rule physicists made up.
Yeah.
It's fundamental to clear communication and, practically understanding things in the real world.
That's exactly it. Using the correct units makes sure our measurements actually mean something. It means we can accurately interpret them, compare them, whether we're in a lab doing experiments or just, describing the weather outside.
Okay, so we definitely see why units are so important. What are some of the, really common fundamental units we bump into in physics?
Well, there are quite a few, but let's focus on the basics for now.
Okay.
For measuring length or distance, we usually use meters, often written as m,
Okay.
or centimeters, centimeters, and kilometers, kilometer. And it's useful to remember how they relate. 1 meter is 100 centimeters, and 1 kilometer is 1,000 meters.
Right. Those are pretty familiar from everyday life, too.
Mm.
What about for measuring how much stuff is in something? Mass.
For mass, yeah, the common units are grams g and kilograms kg, and the key conversion there is that 1 kilogram is the same as 1,000 grams.
Got it. And for time, tracking how long things take.
That's where we use seconds, is, minutes, mine, and hours. And again, the relationships are straightforward. 1 minute is 60 seconds, and 1 hour is 60 minutes.
Simple enough. And temperature, for indicating how hot or cold things are, at least the way we usually talk about it.
Yeah, in many parts of the world, and certainly in the basic physics we're discussing, the standard unit for temperature is degrees Celsius, degrees C.
Okay.
Now, as you get deeper into physics, you'll definitely encounter other units, things like newtons for force, joules for energy. But these basic ones, length, mass, time, temperature, give us a really solid starting point. We don't want to overwhelm anyone just yet.
Absolutely. Definitely best to build this up step by step. So, okay, we've established that these numerals in physics, they kind of go beyond just simple math numbers because of these vital units. Can you expand on that difference a bit more?
Certainly. Think about basic math. You might see an equation like, 2 plus 5 equals 7.
Yep.
It's just a numerical operation, straightforward. But in physics, when we're dealing with measured quantities, the units actually dictate whether a mathematical operation even makes sense.
Okay. How so? Can you give an example?
Oh, yeah. Sure. Let's say you measure a distance of 2 meters. Then you measure another distance of 5 meters. If you add them, you get a total distance of 7 meters.
Right. 2 meters plus 5 meters equals 7 meters. Makes sense.
It makes sense because the units are consistent. You're adding length to length. The addition is physically meaningful.
Okay, combining two quantities of the same kind.
Exactly. But now, what if you tried to add, say, 2 kilograms, which is mass, remember, and 5 seconds, which is time? 2 kilograms plus 5 seconds. What would that even mean?
Yeah, nothing. It doesn't represent anything real. It's like adding apples and hours.
Precisely. It has no physical meaning. Kilograms measure how much matter something has. Seconds measure duration. You just can't combine those fundamentally different kinds of quantities through simple addition like that. It doesn't compute physically.
Right. So the numbers themselves, 2 and 5, you can add them mathematically to get 7. But in physics, the units tell you if that 7 foot actually means anything sensible.
You've nailed it. So in physics, units aren't just labels we sort of tack onto numbers for decoration. They are integral to the physical quantities themselves. They determine how we can legitimately, manipulate them mathematically. For many operations, like addition or subtraction, the units involved must be compatible.
Okay, this is really clarifying things. Let's try and summarize what we've covered. What are the absolute key things you want everyone listening to take away about numerals in physics?
Okay, key takeaways. Firstly, remember that numerals in physics are, well, fundamentally they're numbers, but they gain huge significance when we use them to describe the physical world.
Got it. Numbers with a job to do.
Exactly. Secondly, we encounter those two main types. Pure numerals, just simple counts, and measured numerals. And those measured ones always come with units that tell you the type of measurement.
And the most crucial point, I guess, is about those units.
Absolutely. The units are what give the context, the meaning to the numbers in physics. A numerical value for a physical measurement is basically incomplete, often just nonsensical, without its unit. So the big reminder is always, always include the appropriate units when you're recording physics results, solving problems, anything like that. It's not just about being neat. It's fundamental to accuracy and actually understanding what's going on.
Yeah, I even remember from school, you could lose marks on physics tests just for forgetting the units, even if your number was spot on.
That's totally right. Because think about it, the numerical value alone doesn't fully answer the question about the physical quantity. The unit is an absolutely essential part of that answer.
All right, so we've taken a really insightful deep dive into the world of numerals in physics today. What's the big picture takeaway for you, our listener?
Well, hopefully, you now have a really solid foundation. You understand what numerals are in physics, and maybe more importantly, you get the critical role that units play in making those numbers truly meaningful. And this understanding, it's like a fundamental building block. It'll help you grasp more complex physics concepts as we go along.
And speaking of going along, what exciting topic awaits us next time on the deep dive?
Well, next time, we're going to be delving into the fascinating world of physical quantities themselves, what they actually are, how we classify them, different categories, and the methods we use to measure them accurately.
Oh,
It feels like a really logical next step, right? Moving from understanding the numbers and units to understanding the actual things those numbers and units are quantifying.
sounds like another deep dive we won't want to miss.
Yeah.
Any final thoughts for our listeners as they go about their day?
Yeah, just a little something to maybe think about. I'd encourage you to pay a little closer attention to the units you just naturally encounter in your daily life.
Hmm.
Notice how they provide really essential information about whatever's being discussed. It could be the amount of data on your phone plan, the fuel efficiency of your car, the cooking time on a packet.
Right, they're everywhere when you look.
They really are. And even those seemingly ordinary numbers around you, they hold a deeper physical meaning when you actually consider them together with their units. It's kind of a subtle, but I think a powerful way to connect a bit more with the physical world around us.